our results on the spin and lattice dynamical properties of iron silicide by inelastic neutron spectroscopy. So, iron silicide belongs to a class of transition metal monosilicides which all crystallize in the cubic E20 structure, and the main feature of this structure is that it lacks inversion symmetry. If I talk about transition metals monosilicides, I mean that the transition metal is either manganese, iron, or cobalt. And by investigating the series from MnSi to over FeSi and cobalt silicide, one has insight into many interesting kinds of physics without any change of the crystal structure. So, for example, the MnSi is just a weak itinerant ferromagnet with a helical magnetic order below temperatures of 30 Kelvin, and this order can be suppressed by replacing the 20% of manganese by iron, and one has a paramagnetic metal. Iron silicide itself is a paramagnetic insulator, but by replacing iron by a certain amount of cobalt, one just gets another kind of, the result is just a helical magnetic ordered phase with even higher transition temperatures, which reaches a maximum at around 50 Kelvin at a doping level of 30% of cobalt. And cobalt silicide itself is a diamagnetic metal. So the outline for this talk will be that I just give a short introduction on the properties of iron silicide, a brief introduction on the technique we use, its inelastic neutron scattering, and then I present our results on lattice dynamical and spin dynamical properties of iron silicide, and at the end there will be a short summary. So iron silicide is a narrow gap semiconductor which shares some unusual physical properties with a material class that is known as condom insulators, and therefore it has been claimed that iron silicide is the first 3D electron system that belongs to this class of materials. There's no kind of magnetic ordering, even at very low temperatures, but what is interesting is the magnetic susceptibility, which has some kind of a temperature-induced paramagnetism. Just in temperature-activated behavior at low temperatures with a broad maximum at around 500 K and a cubic isolate decrease at higher temperatures. This has been associated by excitations over a gap, and in a simple two-band model there are very narrow, very narrow bands separated by a gap delta. And at least in the charge response in optical spectroscopy, such a gap opening has been observed. So the opening of the gap sets in at around 250 K, and the gap value just increases with decreasing temperature and reaches around 70 millielectron volts at low temperatures. If iron silicide can be handled as a condom insulator, the explanation for the behavior of the magnetic susceptibility can be explained by excitations from a singlet ground state into a triplet state, and the spin gap should be smaller than the charge gap, and the condom limit just half the size of the charge gap. Another important question is the specific heat of iron silicide. If one compares the specific heat of iron silicide, which is shown as black symbols, as filled symbols, and the cobalt silicide, which is shown as open symbols, there's a difference in a temperature range between 200 and 300 Kelvin, and this has been attributed to the electronic and magnetic or magnetic contribution to the specific heat, but there's the assumption that the phonon contribution to the specific heat should be equal or quite similar for both materials. But however, a detailed analysis of the magnetic contribution to the specific heat is only possible if one has an accurate knowledge about the phonon density of states. So, the technique we use to investigate the lattice dynamical properties of materials and the spin dynamical properties is inelastic neutron scattering, and we performed our experiments on a triple axis spectrometer, which means that we have simply 3 axes that can be moved independently, like that is the monochromator, the analyzer, and the sample angle. And what we measure is the scatter intensity as a function of momentum transfer, which is simply the difference between the incoming and final momentum. And this momentum transfer can be referred to any kind of a reciprocal lattice point and a small vector Q that is inside within the Gaussian zone. And another is the energy transfer, which is the difference between the kinetic energy of the neutron incident on a scattering vector. So if you want to investigate phonons, the main scattering event is due to the nuclear scattering and the interaction of the neutron with the core potential of the within the sample. And another probability, it is affected the neutron carries a spin, and therefore there's a magnetic dipole interaction between the neutron spin and its magnetic moment within the sample, and this kind of scattering is mostly weak in ferromagnets, and therefore we use a technique that is the spin polarized technique, and with the differential method, just meaning that at the sample position we set a guide field either parallel to the scattering wave vector and vertical to the scattering wave vector, and measuring the intensity in both setups in the spin field trend. And from this technique one can derive the full magnetic scattering without any other contributions in the method intensity. So let's have a look on our results for the lattice dynamics. And we measured the phonon dispersion of iron silicide around the 3 main crystallographic directions, which means 111, 110, and 100 direction, and compared our experimental results with calculations based on density functional theory. And along the 111 direction, which is the direction with the highest symmetry, one can clearly distinguish between the 2 transverse phonon modes and the longitudinal modes. And therefore, there's a color coded, the picture is color coded blue and red are the transverse modes and black the longitudinal ones. So the 100 direction has a slightly lower symmetry. That means that it is not possible to distinguish between the 2 transverse modes, but there is one can distinguish the transverse modes and the longitudinal one. And along the 110 direction, no clear selection was applied, therefore no is possible. So for the calculation, we use the experimental lattice constants and the internal parameters have been optimized. That means that the positions of the iron atoms and the silicon atoms have been optimized, and we get an overall good agreement between the calculation shown as solid lines at the experiments. What I have to mention is that the calculation only has been performed at the gamma point and at the zone boundary, while within there's an interpolation that takes into account the phonon behavior, like crossing, and everything that is important. So we have a good picture, a good agreement between experiment and calculation, and therefore we can just calculate the phonon density of states, and it carries out, the result is what is expected, that the iron contributes mainly to the lower part of the phonon dispersion, and the silicon just mainly contributes to the higher energy part of the phonon dispersion. And from this, one can calculate the phonon. Should be possible to calculate the phonon contribution to the specific heat. So in the next 2 slides, I present our results on spin excitations in iron silicide. And as I mentioned, it has been proposed that there is a spin gap to describe the unusual behavior of the magnetic susceptibility. And therefore, we measured the spin excitation spectra at close to reciprocal lattice points that show a large ferromagnetic with large ferromagnetic form factors for the iron atoms. And what we have expected is that the total scattering intensity can consist of 2 parts. One is the ferromagnetic scattering, which is given by mainly Lorentzian shape that's modified with thermal activation with the thermal factor, and contribution from the gap, which is expected to show a behavior like this, that the contribution is 0 till the gap, till the energy of the gap, and then there should be a contribution. But however, and this should lead to something like a change of the mean energy from 0 to higher energies, or at least to an asymmetry of the measured spectra larger than that reduced by the thermal factor. But it carries out that all the spectra from 300 Kelvin down to 50 Kelvin can be described by this simple formula, and the line width of the spectra or of the peaks is constant within error bars for all temperatures. So we only see the quasi-elastic ferromagnetic contribution without any gap signatures up to energies of 80 electron volts, at least for the direct gap. So what one can do is just to integrate over our measured intensity, and that is a quantity that is proportional to the static susceptibility. This is plotted here as filled data points and combined together with older ones from the late 80s, older measurements from the late 80s. One can something like parameterize the static susceptibility by temperature activated behavior with temperature dependent magnetic moment, and the magnetic moment is just plotted here at experimental data, which saturates a 2-Bohr magneton, and it carries out that an activation energy that our data can be explained by some kind of activation energy in the order of 100 millielectron volts. And I have to mention that the red curve, which is our fitted model, is slightly shifted towards, in comparison to the magnetic susceptibility reported in earlier applied measurements, but this one is also sensitive to indirect gaps. So this is where I want to conclude my talk. We have investigated the lattice dynamical properties, we have the model calculations, and these are consistent with the experiments. But however, the spin dynamics, we clearly see the temperature-induced ferromagnetism, but the spin gap just remains an open question. And at the end, I want to acknowledge members of the neutron spectroscopy group in our institute, Andrea Pinchovius, or Veit, who is responsible for the DFT calculations, Willard von Löhneisen, who is my supervisor during my PhD thesis, and Daniela Mago, Ivan Sizis, Jean-Michel Mignot from Laboratoire Léon Villon at CEA, and Alexander Ivanov and Paul Steffens from the Institute of L'Oréal. And you for your attention.
So it's not for questions.
Maybe simple question. Why you choose that particular Q vector?
The scattering is very large around the 110 and the 111. And close to it is that the scattering, the width of the scattering is depends on the Q vector, but the integral remains constant. So we just chose this one as a result from previous.
Then you don't have any momentum scan.
So it remains constant, the integrated intensity. It's cube.
No, integrate on, I mean, you integrate over the frequency. I'm asking momentum scan. Have you done other
No.
momentum? Look at it. Okay.
Your estimate, 100 MeV, how does it agree with previous data for Jacarina, for example, or from optics maybe, or from other estimates?
So the optical spectroscopy results we get at low temperatures of around 70 millielectron volts.
Deep under marrow. Deep under marrow is different from other people. 70, yeah?
In the 60s,
And Jacarina?
it was 65 to 70 millielectron volts.
From other data, same order, yeah?
Yeah, it's quite consistent for
Maybe
the charge
not.
gap. For the spin gap,
Yeah, okay, but I just asked you about pressure.
yeah, the charge gap is around 60, 70 millielectron volts.
Does this material show any of these external-like phases that you see in SI?
FeSi not, but MNSI and cobalt are in lattice. Those given lattices.
So what was, I mean, this, because it's earlier discussion, I'm not sure, but what was the experimental motivation to think that iron Si is a condo insulator? There were some suggestions that you mentioned.
It's been in the early 90s.
So why people think that's a condo insulator?
Because there are properties that are similar. So in condo insulators there are
So the resistivities and so on. Resistivity or transport?
Yeah, the transport measurements and the magnetic susceptibility quite looks the same. Like in, for instance, cerium 3, platinum 4, silicon 3, I think. The shape is the same.
Did I understand correctly that the doped material is a spiral magnet?
Cobalt doped.
Yeah, cobalt doped.
Yes.
So have you done work on that as well?
No, but it's planned.
But it's what? Planned?
We planned, yeah.
Okay. What do you expect to see?
So in MNSI it's been shown that there's a partial order phase present that can be seen in neutron scattering up to 90 Kelvin, the signature of it, and we want just to compare the behavior of cobalt-doped iron silicide with MNSI, whether it behaves similar to it or it's different.
Have the pressure studies been done on this iron silicide?
Is neutron scattering?
Well, any pressure studies, I just don't know, because, you know, on MNSI we know that
I don't know exactly.
okay. I don't know whether it's maybe that the crystals are not big enough or whatever.
The crystals are
Okay,
like
so
this,
they're big for
so-
neutrons, so they're big for everything else, right? Yeah,
Yes.
okay. Because, well, why not? I don't know.
I don't know, and I don't have so much
Okay, great.
data on further components.
If there are no more questions, thank you.